All right, we might get this show on the road at 10:50, so we'll get a few more people trickling in after it starts. So thanks for joining us for the landfill session. In this stream, each speaker has a total of 20 minutes, and at the conclusion of each presenter, I'll be asking questions from the online audience. If there isn't any online, which I'll be checking on the phone, then we'll take one or two short ones from the audience. At the conclusion, all the presenters, I'll bring them up on the stage, and we'll have questions from the audience. The online audience is welcome to text through questions at any time. Please just make sure that your phones are on silent or airplane mode, just so we don't get any buzzing. So we've got 4 great presenters today covering a whole host of landfill issues, from regulatory issues, from lining, from leachate, and transfer stations, which is also a key part of our waste management infrastructure. So to kick us off, we've got Jason Scarborough. Jason's a principal consultant at JS Regulatory Services and is going to run us through a phytocap trial from out in the Midwest. So thanks, Jason.
Okay. Well, good morning, everyone. Forgive me if I'm look like I'm a bit dazed. I'm having flashbacks to 12 months ago where I had the same starting slot for presenters and things got queued up and the technology crashed on me. And for 5 long minutes I had to try and keep the audience occupied with bad jokes, and there was even a suggestion of interpretive dance. So looks like everything's working today, so unfortunately my repertoire of Chuck Norris jokes you might have to miss out on, unfortunately. So I heard someone say, oh, all right, maybe one. There's no theory of evolution, just a list of creatures that Chuck Norris allows to live. There we go. All right, look, back to the business at hand. I'm talking about a phytocap trial that was undertaken with Midwestern Regional Council. And for those of you that are, new to the game or wondering, well, what the hell's a cap to begin with? Well, let's start from first principles, okay? So if we're talking about your average cross-section of a landfill, it sort of looks something like that. A lot of time and attention is often usually paid to the liner system. And then when the facility's about full, people go, holy crap, we've got to put something on top of this now. And there's usually a mad rush to, design and finish off the landfill site while starting either a new cell or a new site. Now, where it gets interesting, phytocap. Some of you might be thinking, a hoobie-waddy. So, look, a phytocap is like what you would call a conventional cap, but basically it incorporates vegetation into the mechanism for its operation. Okay, so it intercepts rainfall, it falls on the cap, and moisture gets sucked out of the cap underneath by the plants, and there's also water storage actually in the soil layer. So it operates by a slightly different principle compared to conventional caps. If you put the two side by side, it sort of looks something like this. So if you follow the New South Wales landfill guidance, you end up with something that can have up to 7 layers of materials stacked on top of each other. And so it can become quite a complex engineering undertaking. You put a phytocap next to it, that's pretty much it. 3 layers of stuff, okay? So from a construction perspective straight away, you can see some advantages there. There's also some, performance advantages as well in operation, maintenance advantages as well. It definitely has merit when you stack them side by side to a conventional landfill cap. So you're probably thinking, well, look, if, they're so good, why aren't they everywhere? And I've done some careful research into this topic, and I thought maybe the difference is in the 2 pathways to get approval for a normal cap versus a phytocap. So if you're going down the road of getting approval for a normal cap, you go to the landfill guidelines, you go have a chat to some engineers, they come up with a design, you go to the EPA, and if they say okay, you build it. Okay, sounds simple enough, but anyone that's been through that journey can tell you that can be arduous, okay, that can be a tough road. For a phytocap, and I think this is where the difference lies as to why they're not everywhere. All right, so again, you start in the landfill guidelines, all right, good start, and they point you to another set of guidelines, which then tell you to get a whole heap of data. and they tell you to feed that data into a computer model. And then out of that computer model, you get a profile design. And then you go to the EPA and say, hey, we want to trial this profile design. They said, yeah, go away and trial that for 3 years. And then you go back into the computer with the trial results and you say, okay, how did we go? Do we need to modify the design? Yes, we do. Okay, go back to the EPA. Here's our trial results, a modified design. And then you go to the engineer and then you can build it. I think that's why they're a little bit trickier to get off the ground. Just a hunch. But anyway, this is where Mid-Western Council comes into the picture here with the Mudgee Waste Facility. And look, it's not a spectacularly unique regional waste facility. It's fairly typical for a mid to large size regional centre. So they're looking to close off their landfill, and there's some challenges to building a conventional cap on this site. So they said, hey, let's have a look at doing a phytocap. So we started off by having a look at the soil that's on site, and straight away we could tell, looking at the analysis of the soil, it's not suitable for a compacted clay liner, but it's potentially suitable for a phytocap, and they've got lots of it. They've got it coming out of their ears, so they're a bit fortunate for a regional waste facility. They've got quite a large amount of potentially suitable material. Oh, and by the way, before monsters go to bed at night, they check under their bed for Chuck Norris. Sorry. There's so many good jokes, I just didn't want to waste them. Anyway. Okay, so we started off the trial and we said, okay, what goals do we need to set? So we looked at 2 goals in particular, okay, and there's one that's specified in the guidance where it says that the infiltration through the cap has to be less than 5% of the annual rainfall. Okay, so that those figures up on the slide there is about what we were looking at for this facility. And then the second one, obviously the big one, is it less resource intensive than building a conventional cap? So they're the 2 things that we needed to tick off on to say, okay, this is worth looking at. So then the next step in the process, we dived into the numerical modelling. And in this case, I used a model called WAVES, developed by the CSIRO, very smart cookies there. Simulates the complex interactions between atmosphere, soil, vegetation, but they need to do a bit of work on their user interface and user experience. It's DOS-based, can you believe that? It's 2023, guys, But, it still provides credible results. Out of that numerical modelling, we got this. Now, it was conservatively designed to work from day one, so it wasn't dependent upon the vegetation to be established and to actually operate effectively. Okay, so in total, 1,600 millimetres of cap with 100 millimetres of what's called a capillary break to stop moisture being sucked out of the waste mass into the actual phytocap. So we did that, we went to the EPA, said, hey, what do you reckon? They said, yeah, go away and test it. And so that's exactly what we did. We put in set up about a 1,200 square metre trial plot using that soil profile, put in soil moisture probes, put in lysimeters, put in an automated weather station, and because it's the 2020s, we put in a system that could actually be accessed online at any time, download the data, view the data, have alerts sent, and all the rest. And what did we measure? Well, everything, essentially, everything that we could. Because my philosophy is that you can never have too much data. So at the end of a 12-month period, there was over 3 million data points, that we could look at. Now, don't worry, I'm not going to go through one by one and bore you to tears, but I will pull out some of the significant findings, which I think are of specific relevance here. We picked a good year to trial this. Apparently it was the 6th wettest 12 months since records began in Mudgee. Okay, so if we're going to give it a trial by, well, I was going to say trial by fire, trial by water, this was definitely it. And in amongst that, there was about a 1.5% AEP storm, 48-hour storm in the middle of that. So, we put it through its paces. And there were some findings interesting findings, and these are the three I'll talk about primarily. We noticed something called what I'm calling a moisture wobble in the soil profile. The response to that storm that I'm talking about was actually quite surprising, and there was some inconsistency between the lysimeters and the moisture probes. So if I bring up the moisture profile first, we deal with that. You're probably all thinking what I was when I graphed this out. What's going on there? Sort of around the 0.75 to 0.95 below ground level. There's something a bit strange going on there. Definitely not measurement related, because this is nearly 81,000 measurements. So whatever's happening there is statistically significant. But we'll come back to that. This is the storm event that I was talking about, that quite intense storm event. So each data point is taken every 15 minutes. So you can see there was quite a lengthy period there where there was 6, 10, 16 millimetres of rain falling every 15 minutes. And the yellow line above it is the soil moisture at 0.75 metres below ground level. And you can see it increased by a whopping 0.7%. Okay, and that was the furthest down the profile that this storm event impacted in the phytocap. And we found that quite surprising given the intensity and the duration of the storm. So, straight away we're thinking, wow, we're onto something here, this works. Then we started looking at some of the lysimeter data, and this is where it got a little bit hinky. So the red line there is infiltration that was measured through the lysimeter, and the blue line, and that graph is rainfall. And you can see there's a couple of peaks that line up, and which was odd, because doing some calculations we figured out that for that to occur, given that each measurement interval is 15 minutes, the phytocap would have to have a permeability equivalent to a well-graded sand, which we knew wasn't the case. Okay, so it was impossible for the water to penetrate that 1,600 millimetres of soil in 15 minutes, essentially. So thinking, okay, yeah, as strange as this is, there's something else going on there. And then having a look at the moisture probes, again, lining up against rainfall events, very little variation in the actual soil moisture that was identified as well. So we're thinking, well, where's this water that's ending up in the lysimeter coming from if, we can't see a progression through the soil profile? So we got to an interesting situation there where we're thinking, okay, if we just looked at the lysimeter data, it fails the first goal that I mentioned before about achieving that infiltration. But if we just looked at the moisture probe data, it passed with flying colours. So we're thinking, okay, there's this questionable relationship going on there. We can't see that deep migration of moisture. That whopping great big storm event didn't penetrate the full depth of the cap. And then that moisture wobble that I talked about. And we thought, okay, something else is definitely happening here. So this is where the benefit of lots of data can come in, because we're able to pull it apart, look at correlations between various things. And we've come up with a theory that we think might explain it. And it might have implications for future phytocap design as well. So basically, this is the principle that phytocaps work on: water in, water out at the top. Okay, so we can model that, we can measure that, not a problem. The thing is we've got this other process happening on underneath, where organics in landfill waste are breaking down, and when they do that, they obviously create landfill gas and they create heat. Again, like delving into the data, okay, looking at temperature down the profile, it's definitely getting hotter the further down we go. Okay, so that makes sense. So the theory being is that, okay, and if anyone's done landfill gas extraction before, they'll tell you that landfill gas comes out humid, comes out quite saturated with water vapour. So we're thinking, okay, perhaps there's water vapour being conveyed from the waste into the bottom levels of the phytocap. Does that explain why it's coming out the other end? Well, it sort of does, because when rain falls, the weight of the cap above it increases, okay, because it obviously absorbs water, and that increases the vertical stress in that soil column, applying pressure, a bit like a sponge. Out it comes, okay? So what we think the data is telling us is that there's this cycle going on at the bottom of the phytocap. Round and round and round it goes. So it's not new moisture, it's moisture that's coming out of the landfill waste, being squeezed out again, coming back up again as water vapour. Okay, so it might mean that the bottom couple of 100 millimetres of the phytocap shouldn't actually be factored into actually working as a phytocap, because it could be that that layer is always going to be saturated from water vapour from the waste. Okay, importantly, this isn't modelled, and I've scoured everywhere to see if there is a model that could describe or attempt to replicate this process. I haven't been able to find one. Okay, so there's a bit of an unknown there in terms of how that sort of bottom couple of 100 millimetres of a phytocap works. So that's probably a good reason why you should be looking at conservative design. Okay, conclusions that we came to from the end of the project. Look, you can never have too much data. It's something I live by. Okay, if you can collect, a couple of more parameters, tighter time intervals, it's worth it. Okay, you can never have too much of it, and when you get apparently contradicting results, that's where it really comes into its own. Yeah, phytocaps do need to be conservative to accommodate for that moisture flux at the bottom of the phytocap. Okay, so as I said, you might have to discount the bottom to a couple of 100 millimetres from that action of how it actually works. Definitely more research required as to what the effects of that is, and hopefully, someone clever can come up with a model that might be able to, replicate that in some form. And lastly, and this is, I suppose, the message for everyone that has an active landfill site in the room, if you've got the right soil type, the main variables that you're looking at now for suitability of phytocap is how much rainfall you're getting and how much evaporation or evapotranspiration you can get. I haven't seen this map, so I'll claim it. Made it up. I'll call it the Scarborough zone. If you're inside that zone, you should be seriously considering a phytocap for your landfill, okay? Because the climatic parameters line up and say that, okay, it should work as long as you've got the right soil type, okay? And all that's left then is the depth. But look, that doesn't mean that it can't work outside of those areas. And, okay, looks like Chuck's having the last say. Well, yes. Okay. Well, that's it for me, thank you. But I do want to acknowledge Mid-Western Regional Council that, they did want to brave that twist and turny path that I showed there before about approvals, and in particular Kylie Stewart and Amber Twin, who have been instrumental in getting this work done. Thank you.
Is it? Where was the hand?
No, thank you for that presentation. Curiosity, with the gas and the moisture coming out of the cap, was that being extracted and controlled, or was that just natural?
That was just natural migration.
So has there been any modelling done if it was extracted and controlled and how that would interact with the cap?
No, there hasn't. Like, you can do the modelling as terms of the impacts of extracting the gas, but as I was mentioning, there's no real mathematical model to, start a baseline with that interaction at the bottom of the cap to begin with. So, but logic would say if you're actively extracting, you'd alleviate that problem somewhat, but not completely. Yeah.
And the phytocap, did Mid-Western Council progress through to looking at their whole landfill and how that might impact on their capital budget?
Yep, and I see Amber's here, she might correct me if I'm wrong. Was it 6 million you're looking at for conventional? I think it was around 6 million. little bit more, 6 million and change. And for a phytocap, probably could be knocked over for less than 2. Yep. That's the active cell that they're capping off, yeah. Yeah. And personally, I think the 6 million and change is rubbery because that would involve compacting high plasticity clays on 1-to-1 batters and things like that, which are, if anyone's ever seen that done, yeah, there we go. Yeah. Don't try it. Yeah. Okay. Thanks, everyone.
Let's get another round of applause for Jason. That was really good, really informative. So our next presenter is Andy Warwick from Global Synthetics. So Andy's going to get up and talk a little bit about our lining and also about maybe some capping at our landfills too using synthetics. So thanks, Andy.
There we go. All right, good morning everyone. So very much like the talk we've just had, this is different processes of landfills. I do like phytocaps, by the way, I'm going to say that, even though this is going to go against it a little bit. So this is about evolution of landfill. Just very quickly, a little bit about our company, if you don't know us. We're a lining company, we're a materials supplier. We have to source 99% of our materials from overseas because there's fundamentally no manufacturing in Australia anymore. Pretty sad, but it's a reality of what it is. There's only a couple of things made here. And it's all geosynthetics. If you're not aware, geosynthetics is really broad. It goes into lots and lots of different things. You've got geotextiles, a lot of people know, HDP liners, geosynthetic clay liners, but it goes way beyond into coastal erosion, all sorts. But as wide as it is, it all sits under these fundamental categories. It separates something, it reinforces it, provides drainage, filters, containment, which is a big thing in landfill and barriers. And this gives you a snapshot of all the different applications we go into. So I was joking with somebody last night that we've got 15 conferences in the next 8 weeks because we're in so many different fields and applications. And we're very lucky in our company. We've got every individual in that photograph is 20 plus years in the industry, so we've got a lot of experience. You can't be an expert at everything. That's the bottom line in our industry, so everyone specialises in their fields. So, the matter at hand, landfill. So back in around about the 1800s, waste was just chucked on the side of the road. It was put anywhere, did whatever you want. But it was actually recycled. Scavengers used to pick it up, recycle it, and do everything with it. Was it the best idea? No, but it was a reality of what they were doing. And then around about the end of the 19th century, they realised actually there's a bit of a health and safety issue with this. People were getting poisoned and there's lots of contaminants and everything going on. So they started to actually try and pick it up and dispose of it. However, what started to happen is in around about the 1920s, all these landfill sites or these areas that they were dumping the waste weren't being controlled. So getting lots of fires, or it was getting washed into the sea or the drinking water, the groundwater, so people were getting poisoned on the back of all of that. So around about the 1980s, they started to engineer landfill sites. They started to actually control where the waste went. They started to control how it was disposed and actually make sure it didn't leak into the ground. And this is an interesting point, especially for a conference like this. In that point in the 1980s, all those polymers that we used were recycled polymers. So your HDPE, which is your geomembrane basis, these are all petrochemical-based materials, recycled. Your geotextile protectant was recycled. Everything was recycled-based polymers. But what this research showed is all the chemicals that were going into that waste, like your chloroforms and that, were actually getting through the membrane system. So while they were trying to build it correctly, they were trying to do everything right, it still wasn't working. It was going into the groundwater and it was poisoning people. I won't name the site, but 10, 12 years ago in Melbourne, they actually had an issue where a landfill site did leak. It did get into drinking water. It did poison people. And ironically, there was no lining in that system at all. And that was only 10 years ago. So a number of things happened. And one of them, this is what now results of best practice today, so to speak, or common. Oh, there we go. The light's blowing up. Maybe a Chuck Norris joke? No? Lost my train now. So yeah, this is generally how they're built now. So you've got a lining system, you've got a secondary lining system, possibly a third, which is a compacted clay. Not very easy to build, but it's part of it. And then they cap it all off and they close it. But the big thing that shifted was everything had to be virgin polymer, because under BEPM guidelines of Victoria and various other regulations, they want a minimum of 120 years, and no manufacturer, designer, will put their hand up and sign off on 120 years with recycled polymer. And I agree with that because it's very hard to control it. Europe was probably the leader in this. It's arguable between Europe and America who actually went first on this regulation. But around about the back end, late 1999, roughly, 2000, this European directive came out, constructive directive. And what that directive kind of came out with was, if it's recycled, you can only warrant it for 5 years. End of story. There was just a carte blanche blanket right across it. So all these recycled polymers overnight were thrown out and they had to get changed to virgin. That increased the cost of the material by 45%. So all of a sudden these asset owners had to find another 45% worth of budget to build their sites, and it was an instantaneous bang, where you go. What they did though is they did put criteria down as to, depending on the waste and depending on what it was, how it could be built. So they talk about non-hazardous versus hazardous. And on the right-hand side, that is actually what they were building before the regulation went on. So they were using separations, they were using base course materials, and they were using drainage for the groundwater or surface water that was coming down. That's a cap design, sorry, I should have said that. That was Europe. So this product here, this was one of the biggest impacted. That's known as a drainage net, to give you an idea. So this collects water or gas, and it takes it to its designated drainage point. They were all recycled, and all of a sudden they had to change. But what they were doing is, on the top right, not the best picture, they were putting drainage stone up the sidewall of a landfill site to catch the leachate and drain it down. So it was their way of controlling and separating leachate from the waste. This net was actually in replacement of the stone. But yet, even today in Australia, only some landfill sites still adopt this. Other ones still put stone up the side, which to me is crazy, and it's impossible to build because you've got to kind of do a tree structure to actually build it. Very difficult. But again, it was the recycle versus virgin which caused this kind of transition. And that's just an idea of what it looks like. It's on a roll, it's easy, it's very quick and very efficient. So this is, even today, this is some of the guidelines that are out there. So here on the left, that's still an adopted practice of waste. You've got a gas control there, you've got your impermeable minerals that they put in there, like a compacted clay, drainage aggregate, and a topsoil. So there's no geosynthetics in there at all, it's all natural materials. But the challenge of that is those materials are getting hard to source and harder, and there are many times where councils and private bodies are struggling to source the clay to actually fit into the bill of these requirements. So on the right-hand side is, let's say, a semi-conservative way of doing it, where they've introduced a geomembrane, so an impermeable layer. They've introduced a geotextile to protect that layer, but they've still got the drainage layers and they've still got filters, so that's still a little bit behind, say, the Europeans and the Americans' methodology of doing things. But again, that's under certain states' guidelines to do that practice. Oh, no. And that's kind of what it looks like for people that haven't seen an active cell construction. Those are the multiple layers, and that's how it actually looks. So you've got the white is like your geotextile, you've got your geomembrane in there, so that's your impermeable layer, and a protection layer to make sure it doesn't get damaged. Now we move on to the next evolution, which was a geosynthetic clay liner. So they're taking a non-woven geotextile either side, and they're putting a bentonite clay in between those two layers of geotextile in a powdered form. When it gets installed, it gets hydrated from the groundwater underneath it. It swells, solidifies, and actually becomes an impermeable barrier on the back of that. And it just naturally rehydrates from all the groundwater and the moisture. Same on the cap, you can do it from groundwater or the moisture from the waste that we just talked about in the phytocap session, the moisture coming out in the gas. So it's another impermeable layer. So what that meant when you came to these designs is taking the traditional, conventional Landfill on the left, transitioning it to the right. You could have your waste, your levelling layer. You've got a drainage net underneath to collect your gas and get it to a designated point. Your GCL is actually doing all the impermeable work. And then you put a net on the top as well to control your surface water runoff, and you can take it off to designated points. That's important because if you have a shallow cap and water sits on top for too long, it puts undue pressure on your cap and then can put stress and strain on the whole structure of the system. So you need to control your drainage and your water. Well, one point I want to add as well, so that's got a metre of topsoil on the left. This one's got 800 mil on there, so less topsoil, less natural resources being consumed. Hang on, I've gone too far. There we go. Whereas on the right, now we can reduce it down to 800 mil. Sorry, I'm jumping slides a bit. So by putting all of these different systems in, you reduce the amount of natural materials going into it. Why that comes in is compacted clay, as we say, is harder and harder to source. And it's harder to get it to a permeability level of 10 to the minus 9. That's a guideline they have to achieve. And a lot of the times they're getting to -7, they get a -8, but they can't hit that -9 figure. It's really hard. And as you said as well, Jason, trying to build a compacted clay liner on a one-on-one batter is bloody impossible, to be honest. So by introducing all of these geosynthetic clay liners in a controlled form, one, you can build it, but two, you're actually reducing your carbon emissions by more than 50%. Massive, massive reductions there. And that now is what today a lot of landfill sites tend to look like. So they've still got compacted clay in the base. They've got a GCL, they've got a HD liner, protection fabric, drainage aggregate, separation. So there's multiple layers in there. But I was talking to Alison earlier, even now there are some sites that are removing the HDPE and they're using compacted clay with an additional coated component on their GCL. So it's an all-in-one system. It's still quite new, it's quite raw, so not everyone's sure about it, and I think it's pretty site-specific. I bring all that up because the United Nations, and I'm sure a lot of people are very aware, have got their 17 key goals that they're all working towards. And our industry is known as a geosynthetic industry, and it's a worldwide industry. So on the back of those 17 goals, the IGS, geosynthetic industry, looked at all of them and said, okay, as an industry, what can we do to actually help with the United Nations goals? And there's a lot of conception because it is petroleum-based, there are plastics involved, so it can be a bit contentious. But one of the biggest things that we find is we get mixed up with single-use plastics, which is microplastics going in the ocean, very big topic these days, and rightly so, versus an engineered plastic that lasts for 120 years and doesn't break down. So that's one thing that we keep getting pigeonholed into, which is probably not really very accurate and very correct. But it does a lot of other stuff. So water quality is a big thing that geosynthetics can do, and this again is landfill and the side of landfill. Wastewater treatment plants, big component of this. But this slide, this is the one I really quite like, and this is all about microplastics. I'm struggling to see the data, but when the landfill site is built correctly, controlled correctly, and actually deposed correctly, their estimate, which is 5 years ago now, is 129 million metric tons of plastic was controlled and stopped going into wastewater and everything else. So if they're built correctly and done correctly, they're actually doing a good job. I know everyone wants to get away from landfill, but that's just a reality. It is doing a good job. Their estimate by 2040 is it's going to go up significantly, and it's actually going to tip the other way. There's going to be more microplastics in the water than there is in landfill because people just aren't controlling it and doing it correctly. We talked about carbon in there, so landfill cap's a big one. You're trying to do compacted clay liners and using natural resource. The carbon emission offset of using geosynthetics is 76% in a cap. So it's a massive, massive saving in terms of carbons and going into the environment. This is the one I really like though. So you can get drainage aggregate that they use. I should have said this before. So under European guidelines, EPA, BEPM, you name it, they all want a 500 mils layer of drainage aggregate at the base of their landfill site. And that's to control the leachate coming out of the waste and keep it separated from the rest of the waste as it decomposes. Well, that's 420 trucks versus one truck of geosynthetic. That just puts it in perspective of how much material you're moving around, how much damage you're doing to your roads and all your emissions. In Europe today, they've knocked that down to 250 mils worth of aggregate. And they've used geosynthetics to replace the drainage capacity of the aggregate. That's Europeans' best practice now. UK's, now that it's left Europe, have changed and they've gone down to 175 mil. They've changed again against Europe. And America's approximately 270, approximately. But Australia is still 500 mil. That's what they're still doing today. Or 300 and sometimes, yeah. It varies from state to state, I'll actually say on that one a little bit. So moving on to the future now, this is an interesting one. So we've seen this slide before, you've got all your compacted clay, you've got all your liners, you've got your aggregates and drainage, everything. But they've also got gas collection wells and they've got inspection sites to make sure the groundwater's not getting polluted and the gas is being controlled. They've got all these systems already in place. So the big thing is, and a lot of people know this, is extracting the gas and converting it into energy. Big, big thing. And that's an example of what they look like when they're set up. So a lot of the infrastructure is actually already there when they build the site. It's not a big investment to take it further forward. And this is what it looks like. They can turn it into fuel, they can turn it into energy, they can do all sorts of stuff with this gas. But here's the thing, this is some stats out of the US, and this is 4 years ago, sorry. They were converting a phenomenal amount, like it was 125 million acres of forests per year they were saving. That's the amount of energy they were converting out of it. And the map shows all the different landfill sites that they're working on. It was ridiculous. And it's, 14.9 billion gallons worth of gasoline they got back. But in Australia, there's only 11% of landfill sites are harnessing the gas. 11% of active sites are doing this. That's it, nationwide. And that's off the government website that we pulled it off. So that's a real shame and a real missed opportunity, in my view. Another one which is becoming more common, I'd say Canada probably led the way on this, is actually turning old landfill sites or closed landfill sites into solar farms. And Canada really, really pushed the barrow on this one. And when I think about Australia and the amount of daylight hours and sunshine hours you have in this country compared to, say, the Europeans, massive, massive missed opportunity. I was speaking to one consultant the other day and he was talking about how a council wanted to turn an old landfill site into a sporting centre, so netball courts, soccer fields, and so forth. The cost of doing that to reinforce that was absolutely ludicrous, and he desperately tried to talk them out of doing it and doing the structure, but they refused. That's what they wanted. They wanted their sports precinct. So the money involved was crazy compared to the usage and what they were going to get out. Whereas if they'd done this, free energy, reduce the energy bill, reduce the energy costs, significant savings. And that's the process, that's kind of what it looks like. So landfill sites have moved on a lot. The phytocaps is something I've always been quite interested in watching because I do think it's a good evolution. I do think it should go forward and be pushed and encouraged. I know there's controls and concerns, but I do think it's the next step as well. But the bottom line is, we have floods, we have disasters, we have fires. Christ, we all know these pictures from last year and 2 years ago. While as much as we want to, we can't get away from landfill sites. You just can't. In the next 20 years, to try and get down to zero waste, I think is virtually impossible. I just don't think it can be done. Only Belgium's the only country I'm aware that ever did it, and they found their waste off to Germany or they set fire to it. That's how Belgium did it. So you are going to need them. So the question is, can you evolve and get better use out of them? And can we revert back to a recycled-based polymer? And will designers take the risk, or will the manufacturers take the risk? It's an interesting question. Hopefully they can, but it's an open one. So the bottom line is geosynthetics are contentious. They are not the best, but they do a lot more good than people probably realise. And that's me in a nutshell. Yeah.
You didn't have any time for questions after Andy's one gone a bit over, so we need to take up the end and take questions up. Sure. Thanks, Andy. All right, so that was great. Our next presenter is Alison Horlyck from GHD. You know, anyone in landfills knows the GHD name, been around for years, so Alison's going to bring some of her technical expertise. Thanks, Alison.
Thank you and good morning. So, I should check this is working first. Oh, that's the one. So the last couple of years has seen unprecedented and relentless rain across the country. We experienced a rare grouping of 3 La Nina events, which has only happened 2 other times in recorded history. And with no time in between these large weather events to release water from dams, there was a limited capacity for any systems to absorb even the smallest amounts of rain. But we weren't getting small amounts of rain, with months of rainfall being dumped in days, and it seemed that rainfall records were being broken with every new rainfall event. So, much of the east and north coast of Australia experienced significant flooding, and our landfills obviously weren't immune to these impacts of prolonged wet weather and extreme events. So back to basics. What do we consider when we look at a landfill and how it generates leachate? Well, the first most obvious one, we get rainfall. It infiltrates through our cap and cover material in through our waste, and number 1 landfill leachate generation. But with incoming waste being more wet, we're probably not seeing as much absorption of water into that waste as we would usually see. So the waste mass is not absorbing the water, we're getting more volume of water, of leachate, out through the bottom of our waste mass. On top of that, in extreme rainfall events, surface water diversion infrastructure can become overwhelmed with the amount of water that's running towards landfill sites. And in extended wet periods and saturated ground conditions, the proportion of water running off is even higher than what you would usually expect to see. With more rainfall, we get more groundwater, potentially more groundwater infiltration into our landfills, and potentially lower levels of evapotranspiration, which Jason was talking about earlier, is a really important component of taking water out of especially vegetated landfill cap systems. So all of a sudden we're getting a lot of water into our leachate collection systems and subsequently into our storage ponds, or whatever our other storage systems are. But when we get more rainfall, we've got more rainfall into our ponds and less evaporation from our ponds, so our ponds are filling up even further. Some of our site's usual disposal mechanisms, irrigation or recirculation back into our waste, isn't working because our landfills are already wet. Our on-site treatment plants might be working all right, but sewer systems might be full and you can't discharge into those, or off-site disposal by tankers into sewage treatment plants might not be available. So all of these together can leave a site at really high risk of regulatory non-compliance, environmental contamination and unplanned financial liability. And the situation's not looking very good. So what can we do to prevent these issues happening at our sites in the future? First and foremost, sites need to have a good site development plan. We need to plan for these things. A good site plan should consider, first and foremost, keeping landfill site open, but looking at the site arrangement to make sure that the location of future landfill areas and the order of landfilling those cells consider the surrounding topography and the proposed waste filling levels to reduce or even avoid altogether the potential for surface water run-on. It also needs to consider optimisation of the active area footprint sizes and reduction of the high infiltration interim capped areas and maximisation of low infiltration final capped areas. So now we have a good plan. It can save a lot of pain in the future. Now, just as a quick example, example site, cell number 1 and 2, this is a little plan diagram I've got here in the bottom right. So cell 1 and 2 are constructed indicatively as shown on this plan, with the base of the cells being about 10 metres below surrounding ground level, all pretty normal to now. So we had interim fill batters where the surface water flow flowed in the directions as shown on the red arrows. Now, for some reason, the next cell that was constructed was cell number 3. I can see Jason shaking his head. Not really sure what they were thinking, but I guess this is a story about the importance of thinking ahead and looking at the landfill as a system. So now all the surface water from these 3 constructed cells were flowing into the next cell, cell number 4. Now this cell accepts relatively small volumes of waste, and so all of a sudden all this surface water was running into an area which when they developed cell 4 was generating leachate. And all of a sudden this poor operator was dealing with a hell of a lot more leachate than they needed to be when they were having these wet weather events because of this giant catchment area all flowing into an exposed leachate collection system. Oh, there's the leachate. So hand in hand with having a good staging plan is to have a realistic leachate management plan. So when we're dealing with leachate management plans and leachate water balance models, we need to consider all the sources of leachate on a site, and that may include contaminated stormwater from catchment areas running into leachate collection systems. Needs to consider the current site arrangement, but also future sites arrangements, which is in relation again to that staging idea that we have already talked about. And then we need to have realistic storage and disposal options. I'll talk about that a little bit more. Needs to be calibrated with site collected data. There's no point in having a model that doesn't actually reflect your site. And it needs to be regularly reviewed and recalibrated as that new data becomes available over time. A good realistic site water balance model will be able to highlight periods of time when more treatment and disposal capacity is required, where improvements can be made, and where to best invest improvements. For older sites in particular, improvements in final cap designs can have a significant reduction in leachate generation and ongoing capital expenditure. Ongoing operational expenditure. And it will also be able to identify stages in the site's development which will be more prone to requiring contingency leachate management measures. But as I said, a model is just a model, and as they say, rubbish in, rubbish out. So the key is really having some good site data, and the more site data available, the more certainty there is about the site's future performance and how it's performing as time goes on. So we will use that historical data to calibrate the model, to understand what happened in the past, and use that to extrapolate what might happen in the future. So when we're considering sizing new infrastructure, it's important to consider that the quantities of leachate will change over time, depending on the weather, the operational footprints, how the site is operated, and how it's designed. When thinking about leachate treatment and disposal options, the quality of the leachate then comes into play. And again, that will change over time too, depending on the type of waste you have and how old that waste is. So just to quickly illustrate the value of a thorough leachate management plan and a well-developed site staging plan, this is an example of a flow diagram that we use to inform a leachate water balance. Now, this is obviously a large, relatively complex system. Most sites wouldn't have a system this complex. But we have lots of sources coming into lots of storage options. And the reason we had to consider all of these sources and storages is because they all feed into one leachate treatment plant and one sewer discharge point. So we had limited site weather data for this site, a relatively small amount of data, but by undertaking a comparison of that data with Bureau of Meteorology data, and scaling the data around a little bit, we were able to give ourselves a longer range of historical weather patterns to consider. We then used a commonly used program for this kind of thing. It's called the Hydraulic Evaluation of Landfill Performance, otherwise known as HELP, to quantify leachate infiltration through a range of current and future proposed cover and capping profiles. We also had to consider the surface water and the groundwater collection system contributions where they were relevant to leachate and surface water and sewer discharge. So we were then able to compare all these results with the site data to get a really good fit for the site in terms of making sure that the model that we had developed was calibrated for the site itself. And we were able to then extrapolate that to future site arrangements and future potential climatic conditions in order to estimate future storage, treatment and disposal requirements. The modelling did identify that the management measures that were in place at the time weren't going to be sufficient for the future predicted volumes, and we could then consider a range of options for how that might be managed into the future. We could look at reducing the capping area, open areas, and cap improvements, increasing the treatment plant capacity size, having additional discharge volumes into the sewer, and also, perhaps a little bit more interestingly, having in-cell storage of leachate during extreme weather conditions. And because we had such a good model, we could stress test a combination of these different measures in order to evaluate the options and provide the owners with the information to allow them to invest in solutions that have the most impact on their future operational expenditure and risk of environmental containment. But the other upside of this process is it ensured that we didn't recommend expenditure on unnecessary infrastructure. So in particular in this case, there was enough storage capacity on the site, and a new stormwater pond or leachate pond wasn't actually going to help the situation. It allowed the owner to plan for future upgrades well before they were required. And we've recalibrated this model a number of times since we first did this work based on new site data to see how our model is tracking, and so far so good. On the other hand, we've had a couple of sites that we've heard of in the last couple of years with large uncapped areas and some surface water separation issues, and both sites relying on evaporation and irrigation for disposal. Their site management plans relied on tankering the leachate in emergency situations, but due to the wet weather and the quality of the leachate treatment plant wouldn't accept those tankers in those wet weather events. So to manage the situation at these sites, They had to fast-track the design and construction of additional leachate storage ponds, which had to be done quickly and at high cost, and probably more importantly, an unexpected and unplanned cost. So this really highlights the importance of contingencies that are reliable and practical for the site. Leachate treatment plants might be, sewage treatment plants might be unpractically far away. Tanker trucks might not be available, the treatment plant might be closed or offline. If there's a floodplain between you, the landfill site, and the sewage treatment plant, you might not actually be able to get there. Now, these are pretty extreme situations and aren't likely to be the case for most sites, but if they are, it would be potentially environmentally and financially catastrophic. So once you have a good plan in place, it's time to implement the plan and keep to the plan. So good site management practices will reduce leachate generation through infiltration by reducing active tip face areas and inspecting and repairing cover and capped areas to maintain those areas of low infiltration where you have them. A few sites we've seen have been experiencing significant leachate seepage from batters in these extreme and extended weather events, which has impacted the surrounding surface water. So now we're not only dealing with typical landfill leachate, you're talking about contaminated surface water as well. So in terms of managing this, removal of low permeability cover soil materials as landfill levels are being raised can help prevent this happening into the future, allowing the leachate to flow more freely through the waste mass and into the leachate collection system. Exposed leachate collection systems are also prone to overflowing in high rainfall events because they're not just not designed to deal with large volumes of water in a short amount of time, and 100% of rainfall that falls on these areas is then leachate, rather than a proportion which is typical for the rest of the footprint area of a landfill cell. So try to avoid it. Good management of the site's surface water management systems is also important for leachate management. We want to make sure we've got good surface water diversion systems upstream and also leachate containment systems on the downstream sides. Suitably sized and lined bunds, drains and ponds to maintain separation of stormwater and leachate in large storm events. And please empty sediment ponds within the design management period. If your pond is full of water, it's not containing anything else. The next component of good management is in the leachate transfer, storage and disposal infrastructure. It needs to be properly maintained. We want to make sure that pumps are working and are the right size or when you need them. Having remote controls, alarms and instrumentation can help allow you to understand what's happening on your site at any time and how it's changing, how it's responding in changing weather conditions. Leachate ponds are designed with a design freeboard. It's a space between the storage volume and the top of your pond to maintain some capacity to hold a lot of water, direct rainfall water in large storm events, and this needs to be maintained as empty to contain those large rainfall events. Having a visible marker on the design storage depth on site can help your site staff see the operational storage limit to make sure you have that capacity to contain large storm events. So I've spoken a lot here about planning and simulating future site arrangements, but our temperature is going up. Rainfall patterns have been undergoing significant change in the recent decades. And while it's important to note that climate variability is inherent in our climate, there are long-term trends emerging. According to CSIRO's 2022 State of the Climate report, rainfall is decreasing across the southern parts of Australia and increasing across much of the northern parts of Australia. But most importantly, heavy rainfall events are becoming more intense, and the intensity of these short duration extreme rainfall events have increased by around 10% or more in recent decades, with larger increases typically observed across the north of the country. The warming climate can cause increased likelihood of heavy rainfall events, with warmer air holding more water. And events where average rainfall, even when average rainfall is expected to decrease, these extreme rainfall events are expected to increase. So Australian Rainfall and Runoff, which is the national guideline document for design storm events, published a guide in 2019 for extreme rainfall events to provide some indication on the magnitude of these impacts. And work is being done across many jurisdictions to understand the seasonality changes as well, which is probably more important for landfill operators and designers in understanding the impacts of climate change on the design of systems on sites. So there's a lot of data up there, but the crux of it all is we're expecting an increase in the order of 2 or 3% by 2030 and about 10% by 2070. So at GHD, we've been working with our clients to look at the risks associated with climate change, and a lot of this isn't required by regulators, but the risk reduction and financial gains can be significant if looking at a site holistically. So we've developed a process where we first build models based on historical information and run this information through a model based on through a range of climate scenarios, and then consider climate change on top of that. And then comparing based on current site observations through to the future potential scenarios, a risk profile can be generated and then the infrastructure designed to suit the client's risk profile. So what are the lessons learnt? Contingencies may not be available during extreme weather events. Roads might be flooded, tankers might be unavailable, and your existing disposal mechanisms might not be available. Existing site plans aren't always followed or fail to deal with these extreme events adequately. Existing modelling may fail to account for all sources during these extreme events, or consider that those increases are linear, when really they're not. And when looking at capping, consideration of future leachate disposal costs isn't always included. So, in summary, prepare for extreme weather conditions, have practical options for storage and disposal, and considering climate change. Thanks.
Great one. Thanks, Alison. I'm sure a lot of landfill operators were lulled into a false sense of security during the drought years, and these last few wet years probably brought a lot of things to the fore. Our last speaker for the session is Esther Hughes, Senior Environmental Consultant at MRA, and Esther's going to be talking about transfer stations, which are an essential part of our waste infrastructure also. So thanks, Esther.
Hello, and thank you very much for having me here. I've got two disclaimers. One is that I work for Mike Ritchie. Many of you know Mike, so yes, I work for Mike. And the other is that this presentation should have been presented by Sean Paul, but unfortunately he couldn't make it. So it's me. Apologies for that. So I'm happy to join you if you want to have a conversation later. I'm quite willing for that. I'm an environmental planner, so I do planning and approvals at MRA. So, and we're going to talk about transfer stations. So this presentation aims... Oh, hang on, let me get this thing. That way. Okay. The presentation aims to provide useful and practical advice to improve the design and operation of waste transfer stations toward a best practice standard. So there's 6 elements here that we're going to consider: safety and risk management, environmental management, sustainability, resource recovery, efficiency, and value for money. MRA came across 3 elements for best practice landfill as transfer station operation, which are safety and environment, efficiency, and resource recovery, feeding into best practice principles. We visited 9 sites in Tasmania. We took along a site checklist to survey the operations and make an assessment there, analyse the results. We identified some priority actions and we developed some recommendations. These are the 9 sites. Gotta love this one. Back. Okay, gotta love the truck, the panel beater's dream down the bottom there with the car in it. That was my favourite, I think, from all of these. So the first major component of best practice is safety and environment. In a transfer station, it's important to separate visitors and operators. It's often a shared environment. And so it's important to make sure that there's a safety separation there between the actual operations of the transfer station and the visitors who are coming in there. There's also ways of preventing harm operationally by drills, supervision, improvements to site conditions, etc. There may be ways to establish some infrastructure prevention, such as a leachate capture system, some conveyors or some fire suppression systems. And then it's also important to ensure that there's access to emergency services, firefighting, drinking water, first aid, and of course training for first aid and first response. In all these matters, you're likely to be guided by the regulations and planning approvals and the licence that you've obtained for your transfer station. And then we also have a list here of some of the human health and environmental concerns, such as fire, air emissions, hazardous waste, falls, traffic, noise, leachate, stormwater, litter, and ecology. So we're going to play a little bit of a game here of what's wrong with this picture. This site perhaps isn't managed so well, and you remember when you're young and you'd circle a few items that perhaps were wrong. Have a quick look at this. You may notice there's no sealed surface, and so perhaps there's an issue there with slipping or falling or with materials migrating into the ground. There's no covered environment. If you have a look at the back there's a fall barrier, but it's not installed. There's a rope at the back which is preventing fall at the back, but it's not installed properly. There's a lack of signage. There's a lack of attendance by any operators. And you can see that there's some batteries on the side there, which, if they leak, could cause a hazard. So I also have a joke. As transfer station operators, you may realise that batteries are not usually very welcome, and that's because they're free of charge. Thank you. This site, in contrast, is much better. It's got a hard stand, it's got a cover. At the back there is a barrier to the tipping of material, and there's better signage, and there's an attendant personnel there. There's a bit of junk on the side that could be removed to better facilitate the operations, but overall much better operations at this site. And I think the point in all this is that design for safety and environment, small changes can lead to big improvements. So the next element of best practice that we looked at was resource recovery. This is a site-by-site approach. There may be some core materials that some transfer stations will take, or most transfer stations will take, and which are in the list there, and some expanded materials. Not everybody is going to take the same materials depending on your site and your location and your staffing and funding. The key to this is to prioritise recycling. There should be some obvious drop-off locations. There should be a unidirectional flow of traffic and an incentivised pricing scheme and good signage to encourage recycling. If there is a resale shop, one should pay attention to making it the presentation attractive and to good management of materials there. Some transfer stations may receive materials that could be mulched, crushed or baled, and that would encourage a size reduction and better management of materials there as well. This one is a site that we had a look at. We did this concept plan for Devonport Resource Recovery Facility. You can see there that the, let's see if this doesn't turn it off. Yep, okay. You enter via Bay Drive and into this area here. And immediately you go to a resource recovery centre where there's a drop-off and metals recycling on the other side. Unidirectional flow of traffic. After the resource recovery centre, the green waste drop-off is up here, and then finally you get to the residual drop-off, and then on the way out you can visit the tip shop by parking in this area and then exit via a designated exit point. Here's just an example of some good infrastructure for transfer stations, a covered area for a reuse drop-off. Photo 2 is this gas bottles, gas bottles storage area. This one contains globes and batteries. And then, of course, you need bunding for liquid material. This reinforces that idea of safety and environmental control, and it also improves the recycling element. The third element for best practice we looked at was efficiency and value for money, and they were broken down into 3 different segments. So financial efficiency may result from adopting a user pay system where weight-based billing is incorporated. It may have an additional capital expenditure which is recovered during the operational savings. Traffic management could be improved, as I said before, by unidirectional flow and easy access for emergency vehicles. And data collection is possible via the weight-based billing improves that, and also there could be a toll booth, and it also improves your reporting mechanisms. So the automation of data reporting can be used for cost modelling also, and the avoidance of the levy. So we're back to our transfer station here, and you can see that there's been some additional weigh bridges installed for data collection. There's an emergency entrance up here, which is a designated entrance for emergency vehicles, and as I mentioned before, the unidirectional flow of traffic to improve efficiency around the site. Okay, so our projects then developed a checklist, and there's an example of that at the bottom of the page. It developed, using the checklist and the best practice principle, developed some priority actions, and the priority actions were then classified into high, medium and low priority with a short, medium and long time frame. And using those, we could develop a roadmap for the transfer station improvements and undergo some additional analysis if necessary, such as cost benefits, cost modellings, some SWOT analysis or a multi-criteria decision analysis. And then we could develop the design further. This is simply another project that we did, and it just incorporates a lot of those principles which I mentioned before. The flow of traffic around the site has been improved. Way bridges and toll booths has been established. Some covered areas around here for the drop-off of materials and recycling. A bit of additional processing in this area here. A few additional pieces of machinery and equipment, and designated areas throughout for different materials. So some of the benefits of this approach would be to expand the life of the transfer station or landfill, increase resource recovery, increase efficiency, improve safety, and better financial management. Thank you.
All right, thanks, Esther. Now, we've got some question time for Esther or for any of the presenters. So we've got a roving mic that's moving around. If anyone has a question, if they'd like to stand up and address it to one of the presenters, we can. It's a little bit tight up here to get all the presenters back up here on stage, but we'll pass the mic over to the presenters once there is a question. So, is there any questions at all? Well, all right, I'll go on. Jason, so let's say you're a council looking into a phytocap. You presented some pretty technical things. What's the smallest and the first step that a council staff could do if they want to, say, learn more, or say get some of the management on board? Is it looking into the soil types, or what does that look like for starting to uncover some of that information?
Yeah, so I did mention some guidance in my presentation from the old waste management, what are they now, WMRR. I think that's a good place to start because that has a lot of good information about what phytocaps are, how they work, and explains the technical aspects in plain English terms. So yeah, if you're looking to get management on board, that's probably a good place to start with that. Yep.
Oh, good one.
Dave Rees, I'm Mid Coast Council. We currently just built a landfill. Tristan actually helped us over here from SMEC, did a good job. We are looking at capping our site, and the conversations we're having with the EPA at the moment, they seem to be trying to push councils towards using GCL, HGP liners. Have you what's the best way to approach that conversation with the EPA if you're looking at an alternate from your perspective?
Yeah, all right, that can be a tricky one. I think the most effective approach is the landfill guidelines set performance goals, and the specified ways to achieve that in their suggestions or exemplary practice to achieve that. If you can come up with an alternative that you can demonstrate achieves those same performance goals, like a phytocap, then there's little room to argue. I mean, if it achieves the same outcome and it's using less materials, it's less carbon intensive, saves you money, reduces your ongoing maintenance costs, it's a pretty hard point to argue that you must do it a certain way. So, yeah.
Do you find that adds extra time, or is it a similar amount of time in the planning stage and the correspondence back and forth with the regulator?
Yeah, look, it is a bit of extra time in that lead up, in that planning and development stage, but you usually get that back in the construction, operation and maintenance phase. So, yeah.
Thanks, mate.
Any more questions? Up, one down in the back there. It's down the back on the right.
Hi, this question is for Andy, I think his name was, about the geosynthetics, just querying the use of the GeoNet. Is that a useful item for when you're lining a new cell for the leachate, or is there too much and you can sort of only use that for your gases and for your surface drainage at the top?
No, you can use drainage nets on the sidewall of your cell. That's a very accepted practice now throughout Australia, so you don't need any drainage stone at all. You just use your GeoNet, and some designers, GHD especially actually, down in Newcastle, they designed the net in such a way that it was a protection fabric against the membrane on one side, and it was a filter on the other side, which was Adrian's job, I remember. In Europe, they're using drainage nets in the base of the cell to replace the aggregate. That's how they're managing to reduce the aggregate. They haven't removed it completely, but they have significantly reduced it. So in short, yes, the nets are being used for leachate collection, gas venting and surface water drainage as a all-in-one, basically.
Thank you.
Question just down here, Linda.
Thank you. This one's to Esther. Esther, in the context of your presentation, what are your thoughts on the Elbin waste transfer system?
Sorry, in terms of...
Sorry, my name's Jason, and it was to Esther.
Yeah. Oh, Esther, sorry. Yeah.
Sorry, Jason.
Sorry, Jason. In the context of...
The Elbin waste transfer system, which is out here in front.
Sorry, could you repeat the question? Sorry.
In the context of a waste transfer station, what are your thoughts on the Elbin waste transfer system, which is being demonstrated out the front of the facility here?
Yeah, I'm sorry. I can't really answer the question because I didn't do the project to start off with, and I haven't reviewed the Elbin waste transfer station. So maybe later we can have a look.
Thanks.
Sorry.
So the L bin is just a way of emptying into a bin?
It's actually a full waste transfer station system. Yeah.
Yeah. Okay, apologies.
In the context of that, what about Jason? Your thoughts on doing that, since you're quick at the gun?
One more question just down the back here, and that'll be our last one before lunch.
Hi, Glada from Armidale Regional Council. My question is for Alison. I wanted to ask, in terms of leachate management, do you think that leachate ponds or having potentially like additional leachate ponds are adequate to managing leachate on site?
It's really site dependent. There's no one size fits all when it comes to the right amount of leachate storage for a site. As I kind of indicated, for some sites, and it really depends on your location, even some sites in normal conditions, a leachate pond is actually a leachate generating piece of infrastructure. I know for a site that I worked on in the Central Coast here in New South Wales, their rainfall is just too high and their evaporation is just too low for larger ponds to be beneficial. So yeah, you do need some storage capacity on site, and for most sites it's part of the disposal mechanisms as well. But yeah, it really has to be assessed on a site-by-site basis.